All right, standard 6.1.6, find limits at infinity. So what this means is we're looking at x as it approaches infinity or negative infinity. So the key here is to be able to either picture or identify or what have you the function's end behavior. And so I'm not going to go into a long thing on end behavior, but we need to be able to take a look at a function and sort of find out somehow what it's going to look like as end behavior. All right, so one of the things, let's just look at the first example that they give. Then I'll write down three of the three general things that you want to look for with a rational function, and then just a couple of other limits as x goes to infinity, and then that's kind of it. Doesn't go, I guess, too much detail here. So right now we've got the limit as x approaches infinity of x divided by x minus 1. So let's take infinity. Right now we can't quantify it, that's why we can't substitute it. But let's just take a large number. Let's just say 100,000. So let's do 100,000 divided by 100,000 minus 1. So 100,000 divided by 99,999 is going to be so close to 1 that a calculator might even round back down to 1, just because it's so close. So we could gather that if x kept getting larger, that it would keep getting closer and closer and closer to 1. So we would say that this limit is equal to 1. So rather than try to picture a very large number and substitute it and find out some kind of answer, there are some things that we can do to help us out here. Namely, what I had kind of noticed was that we had a single x to the first power divided by some function which its leading coefficient was also x to the first power, and then minus a constant. So when I have that, the 1 is so insignificant we can just kind of ignore it. And we have x divided by x. We know that x divided by x is 1. And so that is the end behavior of the function. This function is going to tend to go out as x gets larger and larger and larger. It gets closer and closer and closer to 1. So one way we can look at it is we want to look for the highest degree of x, or of our variable, and try to see if we can make any determinations from there. So the general rule, and now this is not going to be some real high quality mathematical notation, but if we have two functions f and g, and we have the limit as x approaches infinity, then as long as g of x is not 0, I have to throw that stipulation in there, we want to look at the exponents. So if the degree of f, is less than the degree of g, then this limit is going to equal 0. So if we picture that, let's just use an easy function. If I had x squared divided by x to the third. All right, that's going to, if we were to factor out x's, we would be left with 1 divided by x. So as x got really huge, 1 divided by a really huge number gets closer and closer and closer to 0. So anytime the degree of f, the degree of the numerator is less than the highest degree in the denominator, then the limit is going to be 0. And that's going to be true for x going to positive and negative. Infinity. Yes. So when the degree of the highest degree of f in the numerator is less than the highest degree of g in the denominator, then the limit will tend to 0. The next case we've got, so that's case 1. So case 2. So let's say we have the limit as x approaches infinity of f of x divided by g of x, provided g of x is not 0. If the degree of f of x equals, and I should say the highest degree, I've been trying to emphasize that, but I haven't written it down yet, of f of x equals g of x, then the limit is going to equal the coefficient of the highest degree coefficient of f and divided by the highest coefficient, the coefficient attached to the highest degree of g of x. So in all that mumbled stuff, so for instance, it's going to be, let's just call it m and n, where that's the coefficient of highest degree, and the same thing of n. So for example, if I have a function that is 2x to the 4th divided by 10x to the 4th, then my limit, my answer, is going to be 2 divided by 10, otherwise known as 1/5. Alright, so if I have a function that is 2x to the 4th divided by 10x to the 4th, I know that my degree, my highest degree, matches, so that my answer is going to be the coefficient. And why they match? Well, if we just ignore the 2 and the 10, we notice that we have, if we just focus in on our x's, x to the 4th divided by x to the 4th is 1. So 1 times 2 is 2, 1 times 10 is 10. So we end up left with 2 divided by 10. And so even if it has x to the 3rd, x to the 2nd, x to the 1st trailing this thing, so I'm just, don't get confused by this, but if I have this in here like this, those are, when x is really, really large going to infinity, these become insignificant. And so that's the reason we're focusing on the highest degree. They're not going to make that much of a change. That leading coefficient is the one that really does. So we focus on that only when we have a limit, when you see infinity right here. All right, in the last case, case 3. Sorry to be taking so long. Just want to make sure I'm as clear as I can be. So if the highest degree of f of x is greater than g of x, then this limit will be infinity. So, for example, again, if I have x to the 4th divided by x to the 3rd, that leaves me with x over 1, which is just x. And so, as you can imagine, if I plug in a really, really large number, or x keeps getting bigger and bigger and bigger, the function value is going to get really, really, really big. It's going to keep getting bigger. So this is going to be true as long as the degree in the numerator, the highest degree in the numerator, is bigger than the highest degree in the denominator. So these, when we would divide these, we're left with just an x. But if the answer could be x squared, x cubed, and so we know with that it's getting bigger even faster. So our 3 cases, the numerator can have a highest degree that's less than the denominator, and that limit always comes out to 0. We can have a highest degree equal on the numerator and the denominator, and those will come out to be the coefficients of those 2 highest degrees. And we can also have the highest degree in the numerator bigger than the highest degree in the denominator, and that limit will always come out to infinity, because the numerator is going to tend to get bigger faster than the denominator, kind of rendering it insignificant. So what will these look like? Couple problems. So I notice that I have infinity here, so I'm going to look at my highest degree, here, here. I notice that they're the same, 2 and 2. So my coefficients are 4. And since there's no coefficient in front of n squared, I know that that's 1. This 10,000n, in all reality, it's just insignificant. If x is large enough, that 10,000 times whatever that large number is isn't as significant as that large number squared. So we can concentrate on just the 4 divided by 1, and we find that our answer is 4. It's like 3 points. So if we see one of those questions, we should jump all over it. All right, another one here. We have infinity right here, so I look at the highest power. Now notice, they threw a trick here. The highest power is not the first term, so be careful there. Or this term. You got to look through and make sure you identify them. So it's this one. Make sure you include the minus sign, the negative sign. Don't let that slip away. And we also have this one. We notice that they are both 2. So my coefficients are a 1 and a negative 4. And so our answer is negative 1/4. One more for you. Again, infinity, highest degree. Notice that it's 3 over 1, and so we find that our answer is 3. So those are fast. Like I said, if the whole test could be composed of those, it'd be great, but that's not reality. So that is the limit as x approaches infinity. And again, if it's not one of these rational functions, you have to kind of picture end behavior. So to throw it in there, I know we're kind of getting long here, but the limit as x approaches infinity of the sine of x. Sine of x. Well, we can't really pinpoint what's happening to that, because we know that sine oscillates between -1 and 1, depending on what x is. And it is never really going to tend to get to any one value. So we say that this one doesn't exist, because it never really tends to one value. So you just I'm picturing the end behavior of sine on a graph, and we head out to infinity this way, and we're just gonna the whole time. So it's never going to tend to one value. It doesn't exist. It's oscillating. So something like this. Okay, I know that e raised to, as the power of e gets bigger, it just keeps increasing. So I know that that one's infinity. So it's just kind of knowing your end behavior. This one is a good way to kind of introduce negative infinity. So let's say I have the limit as x approaches negative infinity of e to the x. Well, here's the graph of e to the x right here. Let's say it's on the graph. This would be like a value of 1 here. That's 1. And that's not accurate anymore. Let me get rid of that real quick. Okay. Let's quit being so sloppy. So, we have the graph of e to the x. That's 1. Okay, so as x goes this way, and you let x get really, really, really large, negative, all right, what we're going to have a tendency to see is that if we were to do a, we can't plug in infinity, but if we did that, we'd get this, which is the same as saying this. So even though we can't quantify infinity, we know that e to any really large number is going to be really large. We use our laws of exponents. We can write it this way. So 1 divided by a really large number is 0. So the limit as x approaches negative infinity of e to the x is 0. So again, end behavior of the function, just kind of have to picture what the function is doing. What would happen if you stuck in a really large number to that, and just kind of picture what's happening in your head. And that's sort of the way to kind of tackle those ones that aren't the rational functions.